Welcome to Discrete Mathematics. Today, we are going to explore a fascinating and highly practical topic, the equivalence of Boolean polynomials. If you have ever wondered how engineers design incredibly complex computer chips that fit inside your smartphone, understanding this concept is the very first step. Let us dive in and build our understanding from the ground up. To start, imagine you are giving directions to a friend to reach your house. You could give them a complex set of turns or a simple straight path. Both sets of instructions sound completely different when spoken out loud. But if your friend follows either one, they end up at the exact same front door. In the world of digital logic, we have a very similar concept. Sometimes, two completely different looking mathematical recipes will always produce the exact same final result, no matter what ingredients you start with. When this happens, we say these two recipes are equivalent. Now that we have the intuition, let us define this formally. In discrete mathematics, a Boolean polynomial is simply an algebraic expression. But instead of regular numbers, it is constructed using binary variables that can only be 0 or 1. We combine these variables using three main operations. Addition is used to represent the logical OR operation. Multiplication represents the logical AND operation. Finally, complementation, often shown with a prime symbol, represents the logical NOT operation. By combining these, we can build any logical statement. This brings us to the core idea of equivalence. We say that two Boolean polynomials are equivalent if they produce the exact same output value for every single possible combination of input values. To put it simply, if you plug in every possible arrangement of zeros and ones into both expressions, the final column of their truth tables will match perfectly. This means that the two polynomials represent the exact same underlying Boolean function, even if their algebraic structures look completely different on paper. Let us look at how we mathematically represent that two polynomials are equivalent. We do this by stating that the function produced by the first polynomial is equal to the function produced by the second polynomial for all possible inputs. In this formula, P and Q represent two different Boolean polynomials. The variables x1 through xn represent the inputs to these polynomials, which can only take the binary values of 0 or 1. The equal sign tells us that for any specific set of inputs you choose to plug in, the final calculated output of P is identical to the final calculated output of Q. Before we move on, let us see this with a concrete example by proving a famous rule called the absorption law. We want to prove that the polynomial x plus x and y is equivalent to the much simpler polynomial x. We will use the fundamental rules of Boolean algebra to transform the left side into the right side. First, we rewrite the single variable x as x and 1. In Boolean algebra, anything ANDed with 1 remains unchanged, so this is a perfectly valid substitution. Next, we apply the distributive law in reverse. Since both terms share an x multiplied by something, we can factor that x out, leaving us with 1 or y inside the parentheses. Continuing with our derivation, we now look at the term inside the parentheses, which is 1 or y. In Boolean logic, if one of the inputs to an OR operation is 1, the result is always 1, regardless of whether y is 0 or 1. Therefore, the entire expression 1 plus y simplifies directly to 1. Substituting this back, we are left with x and 1. As we established in the very first step, any variable ANDed with 1 is just the variable itself. We have successfully shown step by step that the original complex expression is perfectly equivalent to just x. So, we have proven that this equivalence holds algebraically. This brings us to a visual way to confirm it. The truth table you see here provides a brute force proof of what we just calculated. We list every possible scenario for the inputs, x and y, 0, 0, 0, 1, 1, 0, and 1, 1. We then calculate x and y, and finally the full expression, x or x and y. By comparing the columns, we can clearly see that the column for x and the final column are absolutely identical in every single row. This perfectly confirms their equivalence. Now that we understand the absorption law, let us tackle a slightly more complex example. We want to prove that the Boolean polynomial x plus y and x plus y prime is equivalent to just x. The symbol y prime represents the logical not of y. Our approach here is to expand the expression using the distributive law, just like in regular high school algebra. We multiply the terms out, giving us 4 separate pieces. Next, we simplify the individual pieces. The term x and x is just x. The term y and y prime is 0, because a variable and its exact opposite cannot both be true at the same time. We also rearrange y and x to x and y to make it easier to read. Continuing our simplification, we can drop the 0, because adding 0 does nothing to the expression. This leaves us with 3 terms. Now we look at the last 2 terms, x and y prime and x and y. We can factor out the common variable x from both of them using the distributive law. Inside the parentheses, we now have y prime or y. Since a variable must be either 0 or 1, one of these two will always be 1. Therefore, their OR combination is always exactly 1. For the final steps, we substitute that 1 back into our expression, giving us x plus x and 1. We know that x and 1 simplifies to just x. This leaves us with a very simple expression, x or x. Finally, in Boolean logic, x or x is simply x. We have successfully proven that the original complicated product of sums is entirely equivalent to the single variable x. This shows the incredible power of Boolean algebra to reduce complexity. This mathematical equivalence we just performed leads us to an important question. Why does this matter in real life? In the real world, Boolean polynomials are the exact blueprints used to build computer chips and digital circuits. Every logical AND becomes a physical AND gate, and every logical OR becomes an OR gate on a silicon chip. If an engineer designs a circuit using a complicated Boolean polynomial, it will require many physical gates. This consumes more electricity, generates more heat, and costs more money to manufacture. By finding a simpler, equivalent Boolean polynomial, engineers can build a circuit that does the exact same job but uses far fewer physical components. To summarize our journey today, the equivalence of Boolean polynomials means that two different algebraic expressions represent the exact same logical function. We have seen that we can prove this equivalence in 2 ways, either by showing that truth tables match perfectly or by using Boolean algebra rules to transform one expression into the other. Mastering this concept allows us to simplify complex logical statements. This is not just an abstract math trick, it is a critical skill for optimizing digital circuits and computer software, making modern technology incredibly small, fast, and energy efficient. You now have the foundation to understand digital logic design.